sacrifice took shape without them. At the same time, they were being eliminated from many foods because their presence caused problems with product stability and shelf life. Their absence from our foods and our guidelines is a key, a large and growing number of scientists believe, to many of our health problems, and even our befuddlement about food. I have none of the usual qualifications to write this homage. I am neither a physician who treats the diseases to which people who are deficient in these fats are prone, nor a scientist who has spent a lifetime researching the membranes that these fats call home. But that may be an advantage, since scientists and physicians tend to focus on the one piece of the puzzle they are looking at, and these fats, as it turns out, affect the entire body in many different ways. Rather, I am a science writer, a curious denizen of 21st century America with a long-standing interest in food and the difficulties of being a human omnivore, and I will try to present the big picture. Quite simply, trying to understand health and diet without an appreciation of these fats is like trying to understand earthquakes without knowledge of plate tectonics or motion without knowledge of physics. Until we revise our foods and guidelines to incorporate all that has been learned about omega-3 fatty acids in the past 50 years, our diet will be lacking in a very important way. After I introduce these fats, I think you will begin to see why they deserve this book of their own. This introduction will involve some chemistry, but only what is necessary, and most of which will be familiar to cooks, shoppers, and nutrition-conscious readers. All that readers need to know from the get-go is that fatty acids, the components of fats and cell membranes, are chains of carbons and hydrogens with an acidic group at one end. The first of the omega-3 fatty acids is alpha-linolenic acid, or ALA, the single parent of this family of fats. Found primarily in the leaves and other green parts of plants, alpha-linolenic acid is the fat associated with the complex photosynthetic machinery of plants, the fat that enables plants to capture single photons of light and turn them into sugars, the basis of all life on Earth. Alpha-linolenic acid doesn't play a significant role in animals, for reasons I will soon discuss, but it does give rise to offspring who do work that is every bit as important to animals as photosynthesis is to plants. Like all fatty acids, alpha-linolenic acid is a weak acid. That is, it has a slight tendency to lose a hydrogen ion and develop a negative charge. It has the same strength as a very familiar acid, vinegar, which is not surprising, since vinegar, or acetic acid, is also a fatty acid that is common in living tissues, but too short, just 2 carbons long, to be of use in storing energy or building structures. Fatty acids lose their acidic leaning when they team up with a molecule of glycerol to make triglycerides, the substances we commonly call fats, the substances we cook with and that don't mix with water. In most contexts, we can think of fatty acids and fats as equivalent terms, and we can think of the acidic end of a fatty acid as the hook or the coupling that enables our bodies to move these long, sticky chains of carbons and hydrogens around. It's helpful to understand that all triglycerides have an identical glycerol backbone attached to 3 often different fatty acids, 16 to 22 carbons in length. Whether these triglycerides take the shape of butter, vegetable oil, lard, or suet depends entirely on which fatty acids are involved. Some fatty acids have straight, saturated chains, saturated with hydrogens, that is, and produce solid fats. Others have kinky, unsaturated chains, where some of the hydrogens have been replaced by double bonds between the carbons, and produce liquids. Alpha-linolenic acid has a markedly kinky tail, and the fats in which it is abundant, linseed, canola, and soybean oils, are liquids, even at very low temperatures. But alpha-linolenic acid is not kinky enough for animals, which are faster, more mobile than plants, and animals lengthen and add double bonds to this 18-carbon fatty acid before they put it to work in their tissues. Docosahexaenoic acid, or DHA, is one of several offspring of alpha-linolenic acid, and it is the longest, most desaturated fatty acid in animal tissues. It is the fat that permits